All right, now we're going to work through the 3N analysis for cis and trans diimide. So here is cis diimide. It's the one of the two that belongs to the C2V point group. And ultimately what we're trying to work down to is the symmetries of the vibrations and then to see which of those vibrations are infrared active. To do that, we do a normal mode analysis or also a 3N analysis called 3N because we're going to go in, we're going to put a little set of vectors on each of the atoms. So if we have N atoms, here we have 4 atoms, we'll have 12 total motions of that molecule. We'll go through and subtract out translations, go through and subtract out rotations, and then finally we'll be left with the symmetries of the vibrations. All right, so first thing is to make sure that we have our molecule totally oriented correctly. So C2V, the primary axis, is the C2 axis. It's going to go right through the center of that nitrogen-nitrogen double bond. C2 axis goes there. C2 is our Z-axis. And then beyond that, it actually doesn't matter ultimately whether we decide to put the molecule in the XZ or the YZ plane. So I am going to choose to put this molecule in the, let's see, I'll call this one the Y-axis. Okay, so molecule in YZ plane. Okay, so then that would mean the remaining mirror plane, the XZ, is the one that splits the molecule in half this way. It would be the one that would contain the Z, and then the X-axis would come out at you. Ultimately, the assignment doesn't matter as long as you don't change in the middle, and that's why I like to write these down right away and decide which way that I'm going to put it. Okay, because no choice that we make can make a change on the spectroscopy of the molecule. All right, so and then we're going to go, and it's difficult to draw them exactly on the center of each atom, but we at least need to visualize that we're doing that. We are going in and we're putting a set of 3 axes, an X, Y, and a Z, on each of the atoms. And then we're going to see how each of the symmetry operations of the point group affects those little set of vectors that we have on there. Okay, so I'm going to go ahead and put down here. First, I'm just writing, basically copying from the character table. These are my symmetry operations. C2 about Z, sigma V X Z, sigma V Y Z. Ultimately, this other part here is going to be a little bit different. It's going to be a sigma. It's going to be a sum that we sum across, and a sigma divided by the order of the group. And the order of this group is 1 plus 1 plus 1 plus 1, or 4. Okay, and so what we're working out here first is gamma red. That's a little sort of, looks like the hangman. If you're playing the game Hangman, a symbol looks like this, gamma reducible. And then we're going to reduce that into the irreducible representations. Okay, the first symmetry operation is the identity, and the identity does nothing to the molecule, so of course all of the vectors are left unchanged. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So all 12 vectors are left unchanged. We have a couple little cheats here. So one of them is if a symmetry operation switches the atoms, then none of those vectors count toward the total. And so if I do a C2, the C2 switches these hydrogens and it switches those nitrogens. And so I don't even have to think any further about it. It's moved all of the vectors onto a different atom. And so that one is 0. This first mirror plane that we're going to encounter, the XZ, is going to do the same thing. It doesn't touch any of the atoms, so it switches them all. So its character is also 0. And then finally, this last one's going to require a little work from us. By our definition, the YZ is what contains the atoms. And so all the atoms are left in place, only the vectors are going to move around a little bit. So all of those we're going to have to think about. So what does it do? So again, if this one is y, and this one up here is z, and this one out here is x, if I do a reflection through the yz plane, let's just write it down here so we have a little bit clearer. What's the effect of that? So z is left alone, y is left alone, and x goes into minus x. So z was left alone, y was left alone, and x was reflected into minus x. Well, to get our character here per atom, we sum these. So plus 1 minus 1 plus 1 gives me my total character of plus 1. Plus 1 minus 1 plus 1 gives me plus 1 overall. So I don't go and put a plus 1 down here because this is per unshifted atom. So this same situation happens here, 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 and there. So it happens 4 times in this molecule. So 4 times my plus 1 gives me a character of plus 4 overall there. All right, now we're going to go through and do our systematic reduction and figure out what combination of these irreducible representations sum back to this reducible representation. And I follow the Carter book, and this is the worksheet method that Carter developed. So 12 times 1 times 1. So 12 times the implied 1 that we have here, because there's only one identity, 12 times 1 times what's in the character table here. So that gives me just a 12 overall. The middle ones are going to be boring, so 0 times 1 times 1, because of the 0 it's just 0. 0 times 1 times 1, again 0. And this one, 4 times 1 times 1, gives me 4. Now I'm going to sum. 12 plus 4 is 16. 16 divided by 4 gives me a 4 there. All right, now we need to follow, once we have the A1 or whatever the most symmetric representation is, we need to go up here and follow the pattern of this character table. You'll see what I mean by that. So up here it's 1, 1, 1, 1. So down here to have the same pattern is 12, 12, 12, 12. The middle ones again are boring because it's just 0, so nothing exciting there. Up here the pattern is plus 1, minus 1, minus 1, plus 1. So down here that would be 4, minus 4, minus 4, plus 4. Okay, now I'm going to sum. 12 minus 4 gives me 8. So there's 2 of those. 12 minus 4 again gives me 8, so there's 2 of those. And 12 plus 4 gives me 16, so there's 4 of those. One check that we have here is we need to get it to a total of 12 because we started out with 12 vectors up here. So 4 plus 2 plus 2 plus 4 gives me my 12 back. If I summed it down through here, I'd get 12 back. All right, well, what have I done with all that work? I have my gamma, I'm going to call this now gamma 3n, which is 4 A1s plus 2 A2s plus 2 B2s plus 4, B1s plus 4 B2s. Okay, just went and wrote this. 4 times A1, 2 times A2, 2 times B1, 4 times B2. Now I'm going to subtract out my translations. So what are my translations? I can translate along X, Y, and Z. So I'm going to remove an A1 for the Z. I'm going to remove a B1 because of the X, and I'm going to remove a B2 because of the Y. I'm going to also subtract out my rotations. My rotations up here, that's what this capital R is. This is rotation around Z, rotation around Y, rotation around X. So when I subtract out rotations, I'm going to lose an A2. I'm going to lose a B1, and I'm going to lose a B2 out of the total. So, okay, what's left is the vibrations, because I've taken all of the motions, I've removed the translations, I've removed the rotation, so whatever I'm left with is the vibrations. So 3, A1 plus A2. The B1s here fell out completely. Okay, they all got totally subtracted out. So nothing from those. And then there's 2 B2s that are left. So I'm left with symmetries of 6 vibrations. And we mentioned this earlier, so 3n minus 6 vibrations is what we expect. 3 times 4 minus 6 gives me 6 vibrations. So I'm feeling good about this. I have these vibrations here. All right, one thing that I have left to do, if in the problem I ask you how many infrared active vibrations we have, then those are the ones that correspond to X, Y, and Z. So only A1, B1, and B2. Those are the only vibrations that are infrared active. Any other vibration is happening in the molecule, but we don't see it with our infrared spectrometer. So A1, there's no B1s, and then these 2 B2s. So what do we see? 5 IR active. Okay, we also need to analyze trans diimide. Again, we want to start out by making sure that we've identified clearly where all of our symmetry elements are in the molecule, and that we don't switch any sort of orientation during the time that we're doing our analysis. So this molecule as drawn is totally flat, and it belongs to the C2H point group. It has an inversion center in it. It's one of the ways you can make sure that you're satisfied with the fact that it's C2H, whereas the other, where the cis diimide did not. The inversion center, remember, is to prove something has an inversion center, any atom going from the center of the molecule to that atom, I have to be able to do the opposite and get to the same atom. So if I start in the center in the double bond here and I go to the right, I hit nitrogen. If I go to the left, I get nitrogen. If I go to the right and up, I hit hydrogen. So I need to be able to go to the left and down, and I hit hydrogen. And so this does have an inversion center in it. The C2 axis and the inversion center is right through the bond here. The C2 axis is the Z axis, and it points out of the page. And then finally, that means that the mirror plane, so that sigma H, is right there. And it's not super important for us to know this, but this is the X, this would be the XY plane that it's in. All right, so we're going to do the same sort of analysis again. We're going to imagine going in and dropping our coordinate axes on each of the atoms. Work out the symmetries of all the motions, and then subtract out the translations and the rotations. Just copying the character table again. The order of this group also is 4, so 1 plus 1 plus 1 plus 1 gives me a total of 4 for this group. I'm going to write down my reducible representation. The first part is going to be the same, so identity always leaves all the atoms and all the vectors unchanged. I have 3, 6, 9, 12 total vectors, so that's going to be 12. C2 here is goes through the middle. It doesn't touch any of the atoms, and so when I do a rotation around C2, all the atoms move, and therefore all the vectors move, and so it's 0. Inversion is going to be a similar thing. It's going to switch out the 2 nitrogens. It's going to switch out the 2 hydrogens. All the atoms move, so the character is 0. And then we have a horizontal mirror plane here. All the atoms lie in there, so they're all going to come into play. And it's going to be similar to what we saw before. Now if I have my orientation, I've changed it a little bit. So Z out and X and Y being the plane that the molecule lies in. If I do that horizontal mirror plane, Y is left alone, X is left alone, and Z goes into the negative of itself. And this is the case for any mirror plane. For any atom that's left unshifted, +1 from one of the axes, +1 from the other axis, and then -1 from the third axis. So always, for any atom that's left unmoved, the vectors on that atom give a total character of +1. All right, again, there's 4 atoms, so 1, 2, 3, 4. 4 times 1 gives me a 4. Okay, I'm going to go through and do my systematic reduction again. So 12 times 1 times 1 gives me 12. 0 times anything gives me 0. 0 times anything gives me 0. And then again, 4 times 1 times 1 gives me 4. So 16 divided by 4 gives me 4. So this reducible representation contains 4 Ag irreducible representations. All right, so again, I'm going to follow the pattern. 1, 1, 1, 1, 12, 12, 12, 12. Zeros. So 1 minus 1 minus 1, 1. 4 minus 4 minus 4, 4. 8, 8, and 16. 2, 2, 4. Okay, so my gamma, I'm going to call this 3n. So this is all of the rotations, translations, vibrations of the molecule. There's 4 Ag plus there's 2 Bg plus there's 2 Au plus there's 4 Bu. Okay, again, I'm going to consult my character table and subtract out the translations first. Translations, again, are translations along X, Y, and Z. This one's kind of interesting. So I subtract out an AU. And that's interesting. What's interesting here is I got to go to the BU twice because X belongs to BU and Y belongs to BU. So I'm going to subtract out 2 BUs. 1 for X, 1 for Y. Subtract out my rotations. Similar thing's going to happen up here. I subtract out 1 Ag for rotation around Z. I subtract out 1 Bg for rotation around X and 1 Bg for rotation around Y. So total, I subtract out 2 Bgs. I'll do the math now, and whatever's left here is the symmetries of my vibrations. 3 Ag. I totally used up all of the Bg's, so none of those. I'm left with 1 Au, and I'm left with 2 BUs. Okay, I'm going to go back up to my character table and figure out which of these are infrared active. Be infrared active, it belongs to the same irreducible representation as X, Y, and Z. So the only ones that are infrared active are Au and Bu. Au and Bu. So then this one would have 3 vibrations, which are IR active. Okay, I'm going to pull my other sheet out here and see whether we got a result that we can use here. So for this is for our trans isomer. Our trans isomer, we had 3 vibrations that are IR active. And for our cis isomer, we had 5 that are infrared active. So we should be able to tell these apart by infrared spectroscopy. We should be able to distinguish between trans diimide and cis diimide. All right, we're also going to talk about how symmetry can be used to interpret proton NMR spectra, or C13 spectra. And then the question that I asked you guys, had you look and see how many peaks in the proton NMR you would expect for these different molecules. So 1,2-dichloroanthracene, 2,3-dichloroanthracene, 1,4,5,8 tetrachloroanthracene, and 1,5-dichloroanthracene. So there's kind of just two simple things that you need to do here. First, it's going to be the case for all of them. So any spot that is going to have 4 bonds total. So this has 1, 2, 3. So there's a hydrogen here. Whereas this spot already has 1, 2, 3, 4 bonds to that carbon, and so there's no hydrogen there. So any of these junction sites, so 8A, 8A, 10A, 9A, 4A, those don't have any hydrogens on them because there are already 4 bonds to those carbons. And so only the points here that are numbered without an A are going to have the possibility of having a hydrogen. Okay, so let's go through and we'll just follow our same procedure again, where we find a hydrogen, we put down a label, and then we see if any symmetry operation of the molecule will move that label anywhere else. So this hydrogen right here, I'll just go ahead and label it A. Okay, and so there's no symmetry operation that will move that anywhere else. This is a planar molecule. It has a mirror plane, but all the atoms are in the mirror plane, so it doesn't interconvert any of them. So I'm going to go and put a label B here, and I can do this all the way around. So this is pretty low symmetry molecule, and so every one of those sites is going to be unique. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. I was right in the middle of the molecule here. So there's 8 unique protons in that molecule. Okay, well this next one gets a little bit more interesting. So if I go and I label this one A, well then this label can get carried around at least a little bit. So there is a mirror plane that goes through all of these bonds, and so this A label can get carried down to the bottom there. But there's not a symmetry operation that carries it anywhere else. So I need to make a new label, B. That also can get carried down here to the bottom, B. C, and C can also get carried down to the bottom. And then D. D can get carried down to the bottom. So 1, 2, 3, 4, total of 4 unique protons in that molecule. All right, let's look at this one. So I'm just going to pick a spot here, H, A. Well, there is a C2 axis that goes through the middle of this molecule. Or we could think about using inversion. This is the C2H point group. Either one. So if I think about rotating this whole molecule around, this hydrogen, which is here, would now be over here. Okay, if I rotate this whole thing around, this H becomes this H, and this chlorine becomes that chlorine. There's nowhere else I can move it in the molecule, though, so I need to start with a new label, HB. Rotation would move that one to here. HC. And rotation would move that label up here. And then finally, I'm going to have to use HD. HD. So total 4 labels that I use in that molecule. All right, this is going to be my most symmetric one. I'm going to go in, I'm going to label any random hydrogen, label that one A. There's a mirror plane that goes through the molecule, so I can carry A down to here. But there's also a mirror plane that goes this way through the molecule, and so both of those A's can get carried over to here. And there's no symmetry operation that will move those HAs into these middle sites. So I need to use a new label, which I will label B, so HB, and then my mirror plane will carry HB up here, and so there's 2 unique protons that are in that molecule. All right, so one additional type of question that I will ask you is just to reduce a reducible representation that I've given you. And here's one for the D3H point group. So you need to just take this reducible representation and figure out how many A1 primes, A2 primes, E primes, A1 double primes, A2 double primes, E double primes are in there. You don't need to do anything else with it. So you just want to follow exactly what I'm showing you here. Okay, so I've provided myself with a table here, and so just like with the other ones, I'm going to fill in some information here first. So these are all the symmetry operations. I'm going to write my gamma reducible from up here. I need to figure out the order of my group. So 1 plus 2 plus 3 plus 1 plus 2 plus 3, that's a total of 12. Whatever I get for a sum down here, I'm going to divide it by 12. I'm going to write my irreducible representations. Okay, so from this point, we're just going to follow the pattern of the table up here. First, we'll do the A1 prime because that's all ones, and that'll be the easiest for us to do. So 8 times 1, there's an implied 1 there in the table. We don't say how many, there's 1. So 8 times 1 times 1 gives me 8. 2 times 2 times 1 gives me 4. 2 times 3 times 1 gives me 6. 2 times 1 times 1 gives me 2. 2 times 2 times 1 gives me 4. 4 times 3 times 1 gives me 12. This is going to be a little bit more challenging math here. 12 and 10 more gives me, or 12 and 12 gives me 24, plus 12 gives me 36, so total of 36. 36 divided by 12 is 3. If I did my math wrong, either in my multiplications or in my addition here, and I got 35 or 37 or 33 or something like that, something that was not divisible by 12, I know that I've made a mistake either in the multiplication or in the addition. All right. Now we're going to go about following the pattern of this table, and each one of the columns we're going to have to do some work. So up here the pattern is 1, 1, 2, 1, 1, 2. So our pattern down here is going to be 8, 8, 16, 8, 8, 16. Okay, just following the same pattern. So number, number, double, number, number, double. 8, 8, 16, 8, 8, 16. All right, now 4. Up here we have 1, 1, minus 1, 1, 1, minus 1. So it's going to be 4, 4, minus 4, 4, 4, minus 4. Okay, now for my 3C2, 1 minus 1, 0, 1 minus 1, 0. So 6 minus 6, 0, 6 minus 6, 0. Okay, then our mirror planes, 1, 1, 2, minus 1, minus 1, minus 2. So I have a 2, so it's going to be 2, 2, 4, minus 2, minus 2, minus 4. Then my S's, oh, it gets a little bit more complicated. 1, 1, minus 1, 4, 4, minus 4, and then minus 1, minus 1, 1, minus 4, minus 4, 4. Okay, down to the last one. 1 minus 1, 0, 12 minus 12, 0. Minus 1, 1, 0. Minus 12, 12, 0. Okay, now comes for my math. 12 plus 6 gives me 18. Minus 6 gives me 12. Minus 12 gives me 0. So this has to be some multiple of 12 here. So this is 0 times 12 that we have here. So this one is 0. 16 minus 4 plus 4 minus 4 gives me 12. In there one time. 18 minus 18 gives me 0, so 0. 8 plus 4 is 12. Minus 12 is 0. Plus 12 is 12, so it's in there one time. And then 16 minus 8 gives me 8. Plus 4 gives me 12, so that one is in there one time. This is what I would want at the bottom of your paper. This is what I'm looking for. So gamma reducible is equal to 3a1 primes plus an e prime plus an a2 double prime plus an e double prime. Final thing that we have here is a check. If we want to go back, the easiest check is in the e column. So this one would contribute 3. This one would be 1 times 2, because there's a 2 in the E column. This contributes 1, and this contributes 1 times 2. So 3 plus 2 plus 1 plus 2 is 8. Okay, and so just like what we started with up here, 8, we get 8 out of this. So we know that adding the 3a1 prime plus e prime plus a2 double prime plus e double prime will sum back to give us our reducible representation. So our irreducible representation is composed of those reducible representations.